Hello student, myself Dada Pires from Government Degree College, Chennagiri. Today we are discussing about the Bose-Einstein distribution law. This is the this related to a Davangere University of paper 6th of the 5th semester. Let us see, this topic is come under the statistical mechanics and the subtopic is the Bose-Einstein distribution law. Today we are learn about the Bose-Einstein distribution law and gain the knowledge of these derivations of the Bose-Einstein's distribution law. Today we, after the completing the sessions, we learn about the Bose-Einstein distribution law and their derivations and how can we derive this Bose-Einstein equations. Before going this sessions, we must know that this quantum law which have only quantum means they have particle nature as well as wave natures. That is the quantum laws says sometimes, and they obey diffraction, polarizations like this wave topics, that is quantum laws says. And the Boltzmann entropy law, entropy means the disorder in the system and can be given by the Boltzmann. That is why the Boltzmann entropy theorem is given as equal to k into log p, and usually the Stirling law it gives the log of the factorial of some particles given by, that is log n I factorial is equal to n I log n I minus n is the Stirling law. So, as we move that this Bose-Einstein law, it applies to that particles which should be the identical and indistinguishable, means they are similar, means they have a identical and as well as indistinguishable particles. And this Bose-Einstein's quantum law obeys the quantum laws, and it can have integral spin 0 or 1, integral spin the 0 or 1. That is example for this one, and they can fill any number of particles, and this Bose-Einstein for the examples can consider the helium atoms, photons in cavity, pi meson, phonons in solids. These are used by this example for the Bose-Einstein distributions law. As we move for the derivations, we can say this as the phase space. The phase space means they consist of the momentum coordinate as well as the position coordinate, that is phase space. That phase space is divided into number of elementary regions, and this of having the constant energy, and each region is called a sheet, and each sheet can be divided into number of elementary volumes, that is A cells, and one such we take the sheet Si consist of Si number of A cells, number of elementary cells, and having energy range in the Ei plus and Ei plus Di. So, if let the Ni be the number of the indistinguishable particle is distributed in among the Ai minus 1 cell, the number of permutations of that Ni particle can be given by Ai minus 1 in and A partitions. So, then can be given by Ai into Ni plus Ai minus 1 factorial. So, this the number of permutations of Ni particle in Ai minus 1, that is A into Ni A plus I minus 1 particles. But the cells are arranged themselves, elementary cells are there, that is A factorials, and the particles are arranged. If you consider the particles, they are arranged themselves is Ni factorials. So, then totally we can be hence the number of distinguishable arrangements in the ith sheet. If you consider for the ith sheets, that is A into Ni A factorial minus 1, but this can be ai divided by ai factorial means ai minus ai into ai minus 1, ai get cancelled there, ai minus 1 factorial will be remain. So, that is ni a plus I minus 1 ai minus 1 factorial ni factorial. For the total number of sheet consider, then particles can be the product of their pi into a ni plus I minus 1 factorial and a minus 1 factorial ni, that is a minus is number of as compared to the number of sheets or more, that we take minus 1 can be neglecting there. So, then pi equal to ni plus ai factorial and ai and factorial and ni factorial, product of a and ni factorial. So, for the same consideration as in classical stationary, the probability distributions can be given by this equation, that is p is equal to ni plus ai factorial into ai factorial into ni factorial, and thus put this in Boltzmann entropy theorem, that is S is equal to k into log p, that is log p, p is the value here, p is the value here. So, put this S by k is equal to log of p means ni plus ai factorial divided by a factorial ni factorial. According to Stirling law, log of ni factorial can be given by ni log ni minus ni. So, thus put this value S by k equal to sigma log ni plus ai factorial minus log ai factorial minus log ni factorial. So, after this, let us say apply for this one, S is equal to k into log ni factorial a factorial ni factorial. First apply for this one log ni factorial, that is n factorial means ni into a into log of ni minus ni, that is this one for the Stirling law. We apply for this one as usual ni factorial in log ni minus ni, this type of as we see in the previous slide. So, put this value log ai factorial, that is ai log ai plus minus into minus plus, that is ai, and remaining for the log ni, the log ni, that is ni into log ni plus ni. This is the application of the Stirling law to the both the three words. So, then we can be make it simplify. So, that is ds by k equal to dni log a ni plus dn ni dn. So, some words are will be given out. So, at last there remains log a ni plus a minus log ni. For the steady state, we know that for the steady state ds is equal to 0. So, after differentiation, that one that gives the log a ni plus a minus log ni equal to 0. But this can be determined by the Lagrange's undetermined multipliers, that is log ni minus lambda beta e I equal to 0. Apply where lambda and beta are the constants. We apply for this one that is log m minus log ni means log ni plus a divided by ni, and lambda go outer side, this side means lambda plus beta e I, and simplify this one, and we will be log going crossing the equations. It gets the e to the power of exponential, that is e to the power of lambda beta I, that is ni plus a by ni. So, ni is equal to a into e to the power of lambda beta I minus 1. So, means the formula is ni a by e to the power of lambda plus beta I minus 1 is the required Bose-Einstein distribution law equations. As we see in the previous session, that is about the Maxwell's Boltzmann law, we see only ai and this one, not there is the minus 1, and this Boltzmann-Einstein law we see this is the ai divided by e to the power of lambda beta I minus 1. This is all about the derivations of the, this is the required, this is the required Einstein's, Bose-Einstein's equations, this one. So, this all about, so let us we check some basics multiple choice questions as you must understand level. So, in BE statistics particles are whether it is identical, distinguishable or indistinguishable, both A and C. They are identical and also indistinguishable. They are indistinguishable means indistinguishable means they are same like this. So, distinguishable means changes, but B statistics particles are identical as well as indistinguishable. So, in BV statistics the particle have which type of spin they have, whether they have 0 or 1 spin or integral spin of off or any spin or even spin only. Which one is it have? B statistics particles have 0 and 1 spin only. So, the B statistics obeys, usually they obey quantum laws and does not obey the Pauli exclusion principle and does not obey classical laws or does not have integral spin of. So, it is obey only quantum laws. So, this all about the BE Einstein distribution law. Okay, thank you all.